then this would solve the Boltzmann brane problem, right? Because you basically, you don't have any infinities. You have some sort of finite amount of time before the universe. Yeah. What I'm trying to say is that quantum mechanically we have to do this, or to describe the normal world, we have to use these, or the normal world that we see, that I'm searching for a precise definition of, manifestly obeys these IR and UV cutoffs. And this is specifically because in quantum mechanics, it's the short wavelength oscillations that turn into high energy momentum in a way that is not true in classical mechanics. Does that make sense?
Yeah.
Okay. Yeah.
So I'm sorry, I missed something important. So you have these finite. So if you could resolve, you were saying, what if you and Bob are talking about incompatible things?
Yes.
Can you give an example of what that would look like, just so I understand better what you're?
Yeah. So.
Are you making a different set of measurements?
No, we're not making a different set of measurements. So let's say we've agreed on what the wave function of the universe is. We have some sort of compelling cosmological theory or something like this, and there's some very nice initial state, and everybody likes it. Bob could still choose to calculate numbers that don't seem to correspond to anything that physical.
Is Bob living in the wave function or standing outside? Is he a theorist standing outside and calculating things, or is he a piece of the universe?
Let's say that he's calculating something that's happening outside of causal contact from him. But I think this works out. He could even, even if he says that, what do I want to say? I guess I would say that you could, yeah, so you can always say, well, if Bob's a good physicist, he should only calculate probabilities that are in some sense compatible with his branch. But there's, even if you were to acquire that, there's still many degrees of freedom that, Bob has like a very finite bit rate at which all of his observations can ever come in at. And so there's still plenty of like room in Hilbert space for him to choose projectors that don't really match up with the intuitive notion of branches, of outcomes, even if they formally, yeah, good.
So agree with this past, so agree with this data, but you can still.
That's right.
In the future with all kinds of crap.
That's right.
Yeah.
That's right. And there's something different. Like Bob chooses to do this, and Sam chooses to talk about things that make sense, like blocks sliding down inclined planes and this sort of thing. And there's something different about what Bob's doing about what Sam's doing.
Okay. And this is, you're making the point that this is possible to construct these different pictures.
Yeah, so I'm making the point that it's possible to construct these different pictures. This is like a side motivation that we should know what makes one picture good and one picture bad in a way that is not just intuitive, that is we can make mathematically precise.
So this is something that put me off consistent histories long ago.
Good.
This feature that you're talking about.
Yeah. Yeah, there's one way I...
You already made a conclusion about Boltzmann branes based on that?
Well, so the conclusion about Boltzmann branes comes just from... So I'm going to try to give a as precise as I can definition of branches. But if I just assume that the branches are going to be described by projectors that respect an IR and a UV cutoff, then I can make this conclusion about Boltzmann branes. Or in particular, I can conclude that asking about the probability that a Boltzmann brane happens in 10 to the 10 to the 10 years and 10 to the 10 to the 20 years, this won't fit into any kind of the sample space. So
you're saying you just have a finite cutoff on the Boltzmann brane count?
If I want to make statements that fit in a classical probability space, then I will have a finite number of statements I can make. And so therefore, I cannot talk about Boltzmann branes either happening or not happening arbitrarily far into the future.
You still can have a whole buttload of them, right?
You can still have a whole buttload of them. That's true. That's true. Yes, but for eventually you have to get to a point where trying to say whether they happened or didn't happen has the same, at least mathematical status, as trying to say of whether the electron went through the left slit or the right slit. basically all the different outcomes. What did this Boltzmann brain, did he appear and did he experience something? Those are all, right, because you're in just this equilibrium state. And so they're going to be feeding coherently into future Boltzmann brains. And so the question of like whether this Boltzmann brain experienced something or didn't experience something is going to contribute downstream. So you can't assign classical probabilities to the first one and the second one and all future ones.
I'm digesting that, but maybe you should continue.
Yeah, Adrian?
Yeah, so this is, in many approaches to this question, including mine, there's a slight but real tension between choosing a cutoff, which seems like a good idea, and saying what emerges is objective. The problem being what emerges depends at least very slightly on your actual choice of the cutoff.
Yeah.
Is that going to be true here?
So what I'm going to give you a proto definition of wave function branches. So the first thing is that is separate from trying to conclude something just based off of these IR and UV cutoffs. So, just saying that the branches should respect an IR UV cutoff is like it's just some sort of weak restriction on them. But it already allows us to conclude that the very straightforward Boltzmann brain problem it's more complicated than it would appear. Okay.
It looks like this Boltzmann brain, it's about, you're talking about a more general phenomenon, issues that you cannot make divide up the sample space and something happened now, or didn't happen now, okay, it didn't happen now, but it happened next time, or it didn't happen the first 2 times and happened third time, but it happened
right, I
for now, and so on. So you can't have this kind of.
I can't do that forever. Exactly.
This kind of you cannot project. You can't have this kind of orthogonal projections.
That's right. That's right. That can't go on forever. In order to keep doing that and keep getting finite probabilities that get divided finer and finer, eventually I have to start using arbitrarily large energies and projectors that correspond to that. So now, so I'm like again, I don't have a precise definition of wave function branches to give you, and so they will certainly depend on cutoffs. But I think you can still conclude this statement about the sample space being finite. Is that?
As I said, yeah, that's all fine.
Okay. Okay.
Yeah.
Okay.
It just does seem to be this annoying technical issue that's there pretty much in everybody's way of trying to produce an objective reality.
I see. Yeah, I don't think I'm going to be able to get rid of that. It's my guess, but we'll talk about it more when it comes up. Okay, right. So I am interested in this problem of trying to identify objective branch structure. I don't know if that necessarily means I'm going to be able to hand you with absolute mathematical precision the wave functions of the universe. But let me tell you the sort of things that I would like to be able to do. So the first thing is I would like to be able to recover standard decoherence stories with as much accuracy as we already tell them. So we say right now that decoherence tells us something about the quantum to classical transition, and this relies on kind of knowing what the system is and what the environment is. And of course, this is sort of fuzzy, and a lot of people agree in many cases, but it's not really grounded in anything. We should, at the very least, be able to recover sort of that level of exactness. But hopefully, I'm going to be able to go for a lot more than that. I'll be able to do something that if I'm simulating a quantum system on a computer, I will be able to identify branches, at least approximately up to some epsilon, and that will be able to allow me to run that simulation more efficiently. To literally use less computational resources by finding that structure, even if it's got epsilon errors in it. Okay. So I don't know how many. I guess a lot of people in this audience will not find this very surprising, but I'm always amazed by how few physicists really get this. There's sometimes when you hear about the measurement problem and Schrödinger's cat and Wigner's friend, and people basically always just think of things that are set up by humans, that there's some sort of very special case where we're like measuring a single spin or the decay of a single atom. It's something constructed by a person, and it's like a very rare event. And then you often hear this thing, it was like, well, but in most physical systems, as h bar goes to 0, the de Broglie wavelengths gets very small. And Ehrenfest's theorem, or the h bar goes to 0 limit of the path integral, and basically everything just starts following classical trajectories, except possibly in these rare situations. But this is just not true. Ehrenfest's theorem and this h bar goes to 0 story with the path integral is really something that only can guarantee in a lot of situations that classical states evolve to classical states when you are not chaotic, when you don't have any serious chaotic degrees of freedom, and since just many physical systems generally have at least some of their phase space as chaotic, we are going to generically produce these superpositions. So how does that happen?
So
Yeah.
this could endorse this, your second bullet point. I believe that all randomness we ever experience is that it's quantum by about
Well, that's right. So there's
every single bit of randomness that we experience. I don't want you to figure out, I'm just throwing it out there.
Right. I think properly interpreted that is true. Of course, there are things that appear random to me just because I didn't know about them. Like there are things I can attribute to just not knowing, like subjective randomness. Yes, but
some subtlety with those things.
yeah. So I think this is a good thought example for everyone to have in their head, again, just because some people have heard this story about how the wave function is constantly branching in the sense of Everett, but just to drive home, first of all, to give you a toy model to have in your head, and just to drive home how incredibly ubiquitous this sort of behavior is, you can just imagine that you have something like a double pendulum. So this is like one of the simplest classical systems. If you ever want something that's chaotic, you always have to have at least 2 degrees of freedom. And so this has the minimum number, 2 angles. If you prepare this system and you put it in like an isolated room, and you put it in a minimal uncertainty wave packet, so that basically it's got 2 degrees of freedom, and you gave them a momentum and a position that were all minimally uncertain, but it was in the chaotic part of its wave space, or chaotic part of its phase space. So you lifted it up high enough that it's going to do something non-trivial. Then it will be stretched over the entire available phase space, that which is consistent with the conserved energy, after several multiples of the Lyapunov time. Okay, so if you remember the Lyapunov exponent, or the inverse being the Lyapunov time, is just what you get if you look at the classical phase space, and you're going to have some sort of very generically, or many parts of phase spaces, you take the gradient here that is causing directing the classical paths. Sometimes they will be converging, sometimes they will be diverging, and you will get a time constant associated with this. It is a very macroscopic time constant, so it will, if this thing is evolving along on human time scales of seconds, then the Lyapunov exponents will be, things like seconds. It is surprising that this is not eliminated by taking the classical limit, by which I mean taking h bar goes to 0, as long as you recognize that h bar is very, very small, but it's still finite. In particular, another way to say this is that the time it takes to go from this minimal uncertainty wave packet to a macroscopic superposition is something like the Lyapunov time times a log factor, where this is the scale of the action of the problem, and this is h bar. So it is true formally that as h bar goes to infinity, h bar goes to 0, that this time goes to infinity. But of course, if it's a log in there, then it doesn't really matter, right? H bar is some number. It's 10 to the minus 35 or whatever in SI units. And you just take that log, and it's a factor of 35 or whatever it is. and then you just multiply by a second or whatever the Lyapunov exponent is, and so pretty soon you've got something 35 seconds. Now, this behavior is not true if you don't have any serious Lyapunov exponents. So if you're in a part of the phase space that is near an oscillator, then you can rely on this idea that when h bar goes to 0, you're going to follow classical trajectories, but not the case for chaotic systems.
So, wait, so you're saying that if this is in a room and it's on its chaotic trajectories, then in 5 seconds start getting relativistic speeds and all this crazy stuff?
No, not relativistic speeds. It becomes a superposition. If it was fully isolated, it would become a superposition of being in two different places at once.
Also
It's like a cat, dead or alive, is not relativistic.
Okay. And you're talking about taking the h bar going to 0. But h bar has dimensions.
Yeah, so yeah, that's right. So I'm talking about.
Of course, action has the same dimensions as h bar.
Yeah, that's right.
So they cancel
So
out.
I'm talking. That's right. I'm talking about taking the limit as this dimensionless ratio goes to infinity.
So you also take a limit somehow that the action will change in a way comparable to h bar.
Well, you can keep h bar fixed, and you can consider larger and